Here's something that should be impossible. Light has no mass. A photon weighs absolutely nothing, and gravity, at least the way most people learned about it, is a force that pulls on things with mass. More mass means more pull. So if a photon has zero mass, gravity should ignore it completely. Light should fly past a star, past an entire galaxy, in a perfectly straight line, without bending, without changing, without caring. But it doesn't. Light curves around massive objects. It shifts color climbing out of gravitational fields. It follows bent paths through space near anything heavy enough to warp its surroundings. Something with no mass is being redirected by something that supposedly only works on mass. And here's the part that makes it truly strange. Gravity never touches the light. There is no hand reaching out, no rope pulling, no contact of any kind. So how is gravity doing this without ever making contact? If you find questions like this fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with light itself, because before you can understand how gravity affects it, you need to understand what light actually is. For most of human history, light was a mystery. People knew it existed. They knew the sun produced it. They knew fire produced it. But what light actually was, what it was made of, how it traveled from one place to another, those questions went unanswered for thousands of years. Ancient Greek philosophers debated whether vision worked because your eyes sent out invisible beams that touched objects, or because objects themselves emitted something that entered your eyes. Some believed sight was an active process, your eyes reaching outward. Others believed it was passive, the world reaching in. Nobody had the tools to settle the debate, so it went back and forth for centuries without resolution. The first real progress came when scientists started asking a simpler question. Does light travel, and if so, how fast? In 1676, a Danish astronomer named Ole Romer was studying the moons of Jupiter and noticed something puzzling. The timing of their eclipses, the moments when they disappeared behind Jupiter, shifted depending on where Earth was in its orbit around the Sun. When Earth was closer to Jupiter, the eclipses happened slightly earlier than predicted. When Earth was farther away, they happened slightly later. The pattern was consistent and repeatable. Romer realized this made sense if light had a finite speed. The light carrying information about those eclipses had to travel farther when Earth was on the far side of its orbit, and that extra distance meant extra time. The eclipses weren't actually changing, they were happening exactly on schedule. But the news of them, carried by light, arrived earlier or later depending on how much space it had to cross. His estimate of light speed wasn't perfectly accurate, but he proved something critical. Light is not instantaneous. It moves, and it moves incredibly fast, but not infinitely fast. It takes time to get from one place to another. And that means light is a physical thing, something that travels through space, something you can study and measure and try to understand. Today we know light's speed with extraordinary precision. In a vacuum, light travels at about 299,792 kilometers per second. For simplicity, we usually round that to 300,000 kilometers per second. At that speed, light can circle Earth's equator roughly 7.5 times in a single second. It reaches your eyes from the moon in about 1.3 seconds. From the sun to Earth takes about 8 minutes and 20 seconds. Light is the fastest thing in the universe. Nothing can outrun it. Nothing can even match it. Unless that thing has zero mass. And that detail, that specific requirement, is going to become enormously important. But knowing how fast light travels didn't answer the deeper question. What is light made of? Is it a wave, like sound or ripples on water? Or is it a stream of tiny particles, like bullets fired from a gun? Two competing ideas emerged, and they dominated scientific debate for over 2 centuries. Isaac Newton, one of the greatest minds in the history of science, believed light was made of tiny particles. He called them corpuscles, from the Latin word for small bodies. In Newton's view, a beam of light was a stream of incredibly small, incredibly fast particles shooting through space in straight lines. When light bounced off a mirror, those particles were reflecting. When light passed through glass and changed direction, those particles were refracting. Newton published these ideas in a book called Optics in 1704, and his scientific reputation was so enormous that the corpuscular theory dominated for decades. If Isaac Newton said light was particles, that carried extraordinary weight. Few scientists were willing to challenge him. But there was a competing idea. The Dutch scientist Christian Huygens had proposed that light was a wave, a disturbance that rippled through space, similar to how sound ripples through air. Huygens published this wave theory in 1690, and it explained certain things the particle model struggled with. For instance, when 2 beams of light cross each other, they pass through one another without disruption. If light were made of particles, crossing beams should scatter each other, the way 2 streams of thrown pebbles would collide and knock each other off course. But light doesn't do that. 2 beams cross and continue on as if the other beam weren't there. Waves, on the other hand, pass through each other naturally. You can see this with water waves. 2 ripples cross and each continues on its way, undisturbed. This was a point in favour of the wave theory. For a long time, Newton's particle theory held the upper hand, purely because Newton's authority was so immense. But in 1803, a British scientist named Thomas Young performed a brilliant experiment that changed everything. He shone light through 2 narrow slits in a barrier and observed the pattern it created on a screen behind. If light were particles, you would expect 2 bright bands on the screen, one behind each slit, like 2 clusters of bullet holes. But that's not what Young saw. He saw a pattern of alternating bright and dark bands spreading across the screen. This is an interference pattern, and it is something only waves produce. When 2 waves overlap, their peaks can line up and create a brighter spot, or a peak from one wave can meet a trough from the other, and they cancel each other out, creating a dark spot. Young's experiment showed conclusively that light behaves as a wave. Then came the real breakthrough. In the 1860s, a Scottish physicist named James Clerk Maxwell did something remarkable. He unified electricity and magnetism into a single mathematical framework. Maxwell wrote down a set of equations describing how electric and magnetic fields interact. And when he solved those equations, something unexpected emerged. The equations predicted the existence of waves made of oscillating electric and magnetic fields, waves that would travel through space at a specific speed. When Maxwell calculated that speed, it came out to almost exactly 300,000 kilometers per second, the speed of light. This was not a coincidence. Maxwell had discovered what light is. Light is an electromagnetic wave. It's a ripple in the electromagnetic field, an oscillation of electric and magnetic energy traveling together through space. Visible light, the light your eyes can detect, is just one small slice of a much broader spectrum of electromagnetic radiation. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, they are all electromagnetic waves. They all travel at the same speed. They differ only in wavelength and frequency. Red light has longer wavelengths. Blue light has shorter wavelengths. Radio waves have wavelengths stretching meters or even kilometers. Gamma rays have wavelengths smaller than an atom. But they are all the same fundamental thing: oscillating electromagnetic fields propagating through space at 300,000 kilometers per second. In 1887, the German physicist Heinrich Hertz confirmed Maxwell's prediction experimentally. He built a device that generated electromagnetic waves and another device that detected them across the room. He demonstrated that these waves behaved exactly as Maxwell's equations predicted, reflecting off surfaces, refracting through materials, exhibiting interference patterns, everything light does. The wave theory of light was now firmly established on unshakable ground. Light is a wave, not a stream of tiny bullets. And this is where the problem with gravity begins. Newton didn't just give us a theory of light, he also gave us the first complete theory of gravity. In 1687, Newton published his masterwork, the Principia, and in it he laid out his law of universal gravitation. The idea was powerful and elegant. Every object in the universe that has mass attracts every other object that has mass. The strength of that attraction depends on two things: how much mass the objects have and how far apart they are. Double the mass of one object and the gravitational pull between them doubles. Double the distance between them and the pull drops to 1/4 of what it was. It follows an inverse square law, meaning gravity weakens with the square of the distance. Newton's gravity explained an enormous amount. It explained why objects fall when you drop them. It explained why the moon orbits Earth rather than flying off into space. It explained the precise motions of every planet around the Sun. It predicted the tides caused by the moon's pull on Earth's oceans. For over 200 years, Newton's law of gravity was the gold standard of physics. It was tested again and again, and it passed every test beautifully. It worked for falling apples. It worked for orbiting moons. It worked for planets millions of kilometers away. The entire structure of celestial mechanics was built on Newton's gravity, and it was spectacularly successful. But notice something crucial in Newton's formulation. Gravity acts between objects that have mass. The gravitational force is directly proportional to the masses involved. More mass means more force. And if either mass is zero, the equation gives you zero force. No mass, no gravitational pull. Nothing to attract, nothing to be attracted. The force simply vanishes. Think about what this means for light. Maxwell proved that light is an electromagnetic wave. A wave is not an object with mass, the way a rock or a planet is an object with mass. A water wave is a disturbance travelling through water, but the wave itself doesn't have mass in the way a stone does. The wave is a pattern, a ripple, energy in transit. Similarly, an electromagnetic wave is a disturbance travelling through the electromagnetic field. The wave carries energy, certainly, but under the classical understanding, it doesn't have mass in the way Newton's equation demands. So, if you take Newton's gravity equation and plug in zero for the mass of light, the gravitational force on light comes out to exactly zero. Gravity should completely ignore light. A beam of starlight passing close to the sun should fly by in a perfectly straight line, unaffected, unbent, undisturbed. The sun's gravity should have absolutely no say in the matter. According to Newton, light and gravity exist in entirely different worlds. One has no mass, the other only cares about mass. They have nothing to do with each other, and yet the universe disagrees completely. There is a fascinating wrinkle in this story, though, because Newton himself seemed to sense the problem long before anyone else did. In his book, Optics, Newton posed a series of questions about light, and one of them is striking. He asked whether massive bodies act upon light at a distance, bending its rays. Newton suspected that gravity might affect light after all, and within his own corpuscular theory, this actually made logical sense. If light was made of tiny particles, those particles presumably had some amount of mass, however small. And if they had mass, even a tiny amount, Newton's gravity should pull on them, curving their paths when they passed near something massive like the sun. Newton never worked out the mathematics of this idea in full, but about a century later, in 1801, a German astronomer and mathematician named Johann von Soldner did. Soldner took Newton's corpuscular assumption at face value. He treated light as a stream of tiny, massive particles traveling at the speed of light, and calculated how much their path should bend when passing close to the sun. He used Newton's law of universal gravitation, applied it to these light corpuscles, and arrived at a definite prediction. Starlight just grazing the edge of the sun should be deflected by about 0.87 arcseconds. An arcsecond is an incredibly small angle. There are 360 degrees in a full circle, 60 arc minutes in each degree, and 60 arcseconds in each arc minute. So an arcsecond is 1 over 1,296,000th of a full circle. It is a tiny, tiny shift. But it was a specific, testable prediction, a number you could, in principle, measure if you had precise enough instruments and the right opportunity. The most obvious test would be to observe stars whose light passes near the sun during a total solar eclipse, when the moon blocks the sun's glare and you can actually see the stars behind it. Soldner's calculation was published and then almost immediately forgotten. It sat in obscurity for over a century. But the deeper problem wasn't that his paper gathered dust. The deeper problem was that the entire foundation under his calculation collapsed. Maxwell showed that light is a wave. Young's double-slit experiment demonstrated wave behavior. Hertz confirmed electromagnetic waves in the laboratory. The corpuscular theory of light, Newton's idea that light is made of tiny, massive particles, was scientifically overthrown. The consensus was now clear and overwhelming. Light is not made of tiny bullets with mass. It's an electromagnetic wave, and waves don't have mass in the way Newton's equation requires. This pulled the foundation out from under Soldner's calculation entirely. If light has no mass, you cannot use Newton's gravitational formula to predict how it bends. The formula gives zero force. No force, no bending, no deflection. The only theoretical framework that had allowed gravity to interact with light, Newton's corpuscular theory, had been dismantled by Maxwell's electromagnetic theory. There was no remaining mechanism within Newton's physics for gravity to affect light at all. The story could have ended there. Gravity affects things with mass. Light has no mass. Therefore, gravity does not affect light. Case closed. Move on to other problems. But the universe, as it often does, had other plans. Here is the complication that deepens the paradox instead of resolving it. In 1900, the German physicist Max Planck discovered that energy is not continuous. It comes in discrete packets, tiny bundles he called quanta. Then, in 1905, Albert Einstein took Planck's idea further in a direction nobody expected. Einstein showed that light itself is quantized. A beam of light is not just a smooth, continuous wave spreading through space. It's also made of individual packets of energy, called photons. Each photon carries a specific amount of energy determined by the light's frequency. Higher frequency light, like ultraviolet or blue light, carries more energy per photon. Lower frequency light, like red or infrared, carries less. Einstein demonstrated this through his explanation of the photoelectric effect, the strange observation that shining light on certain metals ejects electrons from the surface. The puzzling thing about this effect was that increasing the brightness of low-frequency light never ejected any electrons, no matter how bright you made it. But even dim, high-frequency light ejected electrons immediately. This made absolutely no sense if light was purely a continuous wave. A brighter wave should deliver more energy, enough to knock electrons loose eventually. But it made perfect sense if light came in individual packets, photons, each carrying a fixed amount of energy determined by its frequency. A low-frequency photon simply didn't have enough energy to knock an electron free, no matter how many of them you threw at the metal surface. But a single high-frequency photon had enough energy on its own. Einstein's explanation of the photoelectric effect was so important that it earned him the Nobel Prize in Physics in 1921. Remarkably, he did not receive the Nobel for relativity, which many physicists still considered too theoretical and insufficiently verified at that time. He received it for demonstrating that light comes in discrete energy packets. This discovery, more than almost any other, forced physics to confront the deeply strange quantum nature of light. This created an extraordinary situation. Young's experiment had proved light is a wave. Maxwell's equations had proved light is a wave. Hertz's experiments had proved light is a wave. And now Einstein had proved light is also made of particles. Not one or the other, both. Light is a wave when it propagates through space, spreading out, interfering with itself, diffracting around edges, behaving exactly like a wave should. But light is also particles when it interacts with matter, delivering its energy in discrete packets, one photon at a time, each carrying a fixed amount of energy. This is wave-particle duality, and it is one of the strangest discoveries in the history of science. Light is not a wave that sometimes looks like a particle. It is not a particle that sometimes looks like a wave. It is something genuinely new, something that doesn't fit neatly into either category, something that behaves like a wave or a particle depending on how you observe it. The universe doesn't care that this seems contradictory. It simply is what it is. So light is particles after all, but not the kind Newton imagined, not even close. Newton's corpuscles were supposed to be tiny objects with mass, like incredibly small, incredibly fast bullets. Photons are fundamentally different. A photon is a quantum of electromagnetic energy. It has energy. It has momentum. It exerts pressure when it strikes a surface. But it has zero rest mass. Not a tiny mass. Not an almost zero mass that we haven't measured yet. Exactly zero. A photon at rest, if such a thing could exist, would have no mass whatsoever. Of course, a photon is never at rest. Photons are born at the speed of light, and they travel at the speed of light until the instant they are absorbed. There is no such thing as a stationary photon, or a slow photon, or a photon coasting at half speed. Photons exist only at the speed of light, and their rest mass is precisely, fundamentally, zero. And this brings us right back to the paradox, but now with the stakes raised even higher. Under Newton's framework, gravity is a force between objects with mass. A photon has zero rest mass. Therefore, Newton's gravity should exert zero force on a photon. A beam of light should be completely immune to gravity. It should pass through the most intense gravitational fields in the universe, past the most massive stars, past the densest galaxies, without so much as a flicker of deviation. But we know for an observed fact that it does not. We have seen starlight bend around massive objects. We have measured shifts in light's energy as it climbs away from gravitational fields. Gravity does something to light, something dramatic, something measurable, and it does it without ever making physical contact. No collision, no push, no pull in the Newtonian sense. There is no hand reaching out to grab the photon. There is no rope. There is no surface touching another surface. The gravity and the light never make contact, and yet the light's path changes. Newton's gravity simply cannot explain this, and the failure is not a small numerical error you could fix with a correction factor. It is a fundamental conceptual breakdown. Newton's framework says gravity is a force between masses. Light has no rest mass, so according to Newton, there should be no effect, none at all. Yet the universe insists there is one, and a significant one. Even if you try to rescue the Newtonian picture by granting light an effective gravitational mass through Einstein's famous relationship E equals mc squared, which does connect energy and mass, you can assign a photon an effective mass based on its energy and run it through Newton's equations. And if you do, you recover Soldner's old answer. About 0.87 arc seconds of bending for starlight passing the edge of the sun. But when scientists eventually measured the actual bending, they found roughly 1.75 arcseconds, twice Soldner's prediction. The Newtonian calculation, even when you generously give light an effective mass it technically doesn't have, still produces only half the observed deflection. The real universe bends light twice as much as Newton's gravity predicts. Something is fundamentally missing. Not a detail, not a refinement, a piece of the puzzle that Newton never had. This tells us something profound. The problem is not with light. Light is what it is, massless photons traveling at 300,000 kilometers per second. The problem is with our understanding of gravity. Newton gave us a magnificent description of what gravity does. Objects with mass attract each other. The force follows an inverse square law. You can calculate orbits, trajectories, tides, eclipses, all with extraordinary precision. Newton's gravity is an incredible tool, but Newton never explained how gravity works. He never described the mechanism. How does the sun, sitting 150 million kilometers away, reach across empty space and pull on Earth? What carries the force? What mediates the interaction? There is nothing between the sun and Earth but vacuum, yet somehow the sun's gravity grips our planet and holds it in orbit. Newton was fully aware of this gap. He wrote that he framed no hypotheses about the underlying cause of gravitational attraction. He could describe the effect with precision. He could predict where planets would be centuries into the future. But the mechanism, the actual explanation for how gravity reaches across empty space and acts on distant objects, remained a complete mystery. And when it comes to light, that missing mechanism becomes absolutely critical. Because whatever gravity truly is at its deepest level, it clearly does something to massless photons that Newton's force between masses framework cannot account for. The conceptual foundation gives no room for the effect to exist, and the mathematics, even when stretched as far as they can go, gives exactly half the observed result. Gravity is not what Newton thought it was. It's not a force pulling on mass across empty space. It is something else entirely. Something that can redirect light without touching it. Something that can shift a photon's energy without friction or contact. Something woven into the fabric of space and time in a way Newton never imagined. What we need is a completely new understanding of gravity. Not a correction to Newton, not an upgrade or a patch, a revolution. We need to rethink what gravity actually is from the ground up. And when we do, the paradox of how gravity changes light without touching it will not just be resolved, it will become obvious. The revolution began with a single thought. Not an experiment, not a calculation, a thought. And the man who had it was Albert Einstein. In 1907, 2 years after publishing his special theory of relativity and his explanation of the photoelectric effect, Einstein was sitting at his desk at the patent office in Bern, Switzerland, when an idea struck him. He later called it the happiest thought of his life. The thought was this: a person falling freely feels no gravity. Imagine standing on a bathroom scale in an elevator on the top floor of a very tall building. The scale reads your normal weight. You feel your feet pressing against the floor. Your body feels heavy. Everything is normal. Now imagine the elevator cable snaps and the elevator begins to fall. You, the scale, the elevator, everything inside falls together at the same rate. The scale drops away from your feet at the same speed you drop toward it. Your feet no longer press against anything. The scale reads 0. You feel weightless. You are still inside Earth's gravitational field. Gravity hasn't disappeared. The ground is rushing up toward you, and in a very short time, the situation will end catastrophically. But during those few seconds of freefall, inside that elevator, you cannot tell the difference between falling in a gravitational field and floating in empty space far from any massive object. Every experiment you could perform inside that closed elevator would give the same result whether you were falling toward Earth or drifting through deep space with no gravity at all. Drop a ball and it floats beside you. Pour water and it forms a floating sphere. Stand on a scale and it reads 0. Jump and you don't come back down. Every single test produces the same outcome. Free fall and the complete absence of gravity are indistinguishable from the inside. This is the equivalence principle, and it sounds simple, maybe even obvious. Of course you feel weightless when you're falling. Astronauts on the International Space Station float around in apparent weightlessness, and they're still well within Earth's gravitational field. The station orbits only about 400 kilometers above the surface. Earth's gravity at that altitude is still about 90% as strong as it is on the ground. Those astronauts aren't beyond gravity's reach. They're in freefall, continuously falling toward Earth while moving sideways fast enough that they keep missing it. That's what an orbit is. Perpetual freefall. And in that freefall, they experience no sensation of gravity at all. But Einstein saw something deeper in this simple observation, something most people would walk right past without a second thought. He saw that the equivalence works in both directions. Here's the other side. Imagine you're in a closed room with no windows. You feel your feet pressing against the floor. You feel heavy. You drop a ball and it falls to the ground. Everything behaves exactly as if you were standing on the surface of Earth. But are you? You might be. Or you might be in a rocket ship deep in empty space, far from any star or planet, accelerating upward at 9.8 meters per second squared, the same rate at which objects accelerate when they fall near Earth's surface. The acceleration of the rocket pushes the floor up against your feet, creating the sensation of weight. Everything inside the rocket behaves exactly as it would in a gravitational field of the same strength. Drop a ball and the floor accelerates up to meet it, which from your perspective inside the room looks exactly like the ball falling down. Pour water and it flows to the bottom of the container. Stand on a scale and it reads your normal weight. From inside that closed room, you cannot tell whether you are standing on the surface of a planet with gravity pulling you down, or inside a rocket accelerating upward with the floor pressing against you. No experiment you could perform would distinguish between the two situations. They are physically equivalent. Gravity and acceleration produce exactly the same effects. Einstein realized this wasn't a coincidence. It wasn't a quirk or an approximation. It was telling us something fundamental about the nature of gravity itself. If acceleration perfectly mimics gravity in every possible way, if no experiment inside a closed room can distinguish between them, then maybe gravity and acceleration are the same thing. Maybe what we experience as the force of gravity isn't really a force at all. Maybe it's something much stranger. But before Einstein developed the full picture, he used the equivalence principle to make an immediate prediction about light, and this prediction strikes directly at the heart of our central question. Go back to that closed room, the one accelerating through empty space. You're inside, and everything feels exactly like gravity. Now imagine a small hole in one wall, and a beam of light enters through that hole, traveling horizontally across the room toward the opposite wall. Think carefully about what happens. The light enters the room and begins crossing it. Light travels extraordinarily fast, 300,000 kilometers per second, but the room has some width, so the crossing takes a tiny fraction of a second. During that tiny fraction of a second, the rocket is accelerating. The room is moving upward faster and faster. By the time the light reaches the opposite wall, the room has moved upward slightly compared to where it was when the light entered. The light hits the far wall at a point slightly lower than where it entered. From your perspective inside the room, the light didn't travel in a straight horizontal line. It curved downward. The beam entered at one height and arrived at a lower height, tracing a slight downward arc through the room. You would see the beam of light bend. Now here is where the equivalence principle delivers its punch. If acceleration and gravity are truly equivalent, if no experiment performed inside a closed room can distinguish between them, then the same thing must happen in a gravitational field. If light curves downward in an accelerating room, it must also curve downward in a room sitting on the surface of Earth under the influence of gravity. Gravity must bend light. And notice something critical about this argument. It never once mentioned mass. The conclusion does not depend on whether light has mass. It doesn't need to. The equivalence principle says gravity and acceleration are identical in their effects. Acceleration bends the path of light because the room moves while the light crosses it. Therefore, gravity bends the path of light. The photon's mass is completely irrelevant. Whether a photon weighs something or absolutely nothing, the bending must occur. The equivalence principle demands it. This was Einstein's great breakthrough on the question of light and gravity. You don't need light to have mass for gravity to affect it. You need something else entirely. You need a completely new understanding of what gravity actually is. And that understanding took Einstein another 8 years of intense intellectual struggle to fully develop. He later said that compared to general relativity, special relativity was child's play. The difficulty was not just mathematical, though the mathematics was ferocious. Einstein needed an entirely new kind of geometry, a geometry in which space and time could bend and flex and respond to the presence of matter. The flat, rigid geometry of Euclid that every student learns in school was useless here. Einstein needed curved geometry, the mathematics of surfaces and spaces that warp and stretch. He spent years teaching himself this branch of mathematics called differential geometry and tensor calculus, often struggling with equations that filled pages and led to dead ends. He made mistakes. He published preliminary results that turned out to be wrong. He followed paths that seemed promising and then collapsed. At one point, he thought he had the final equations and announced them, only to realize months later that they were flawed. He described the process as groping in the dark, searching for a structure he could feel was there but couldn't yet see clearly. The physical intuition, the equivalence principle, pointed the way. But translating that intuition into a precise mathematical framework that could make testable predictions required years of grinding, often frustrating work. It was, by Einstein's own account, the most intellectually demanding thing he ever did. The result, published in 1915, was the general theory of relativity, and it is one of the most profound intellectual achievements in all of human history. Here is the core idea, and it overturns everything Newton assumed about gravity. Newton imagined space as a fixed, rigid stage on which objects moved around. Space was like an enormous empty room, the same everywhere, unchanging, providing a background against which events happened. Things existed in space. Things moved through space. But space itself was just the container, passive and unresponsive, like the walls of a theatre that don't care what play is being performed inside them. Time, in Newton's picture, was separate from space and equally rigid. Time flowed at the same rate for everyone, everywhere, always. Whether you were standing on Earth's surface or sailing through deep space, whether you were sitting still or moving at tremendous speed, time ticked forward at the same steady pace. 1 second for you was 1 second for everyone else. Time was a universal clock, and it never sped up, never slowed down, never varied. Einstein demolished this picture entirely. Space and time are not separate things. They are woven together into a single, unified structure that physicists call spacetime. You exist in spacetime right now. You have a position in space, a location you could describe using 3 coordinates: left and right, up and down, forward and backward. But you also have a position in time. This moment, right now, is a specific location along the time dimension. Your full address in the universe requires not 3 coordinates, but 4. 3 for space and 1 for time. Together, they define a single point in space-time, a specific where and when. This is not just a mathematical convenience or a clever way of labeling things. It reflects something physically real about the structure of the universe. Space and time are genuinely interconnected. How you move through space affects how you move through time. A clock on a fast-moving spacecraft ticks slightly slower than a clock sitting still on Earth's surface. This isn't a mechanical problem with the clock. Time itself passes more slowly for the moving clock. 2 events that happen simultaneously for one observer may happen at different times for another observer moving at a different speed. Space and time are entangled with each other in ways Newton never imagined. Einstein showed all of this in his special theory of relativity in 1905. But in special relativity, space-time is still flat. It's still a fixed backdrop. More sophisticated than Newton's rigid space plus separate time, but still a stage that doesn't respond to what's happening on it. The actors perform on the stage, but the stage itself doesn't change. General relativity changes that. In general relativity, space-time is not rigid. It's dynamic. It can bend, stretch, warp, and curve. And the thing that causes it to curve is mass and energy. Place a massive object like a star in space-time, and the space-time around that star warps. The geometry of space and time near the star is different from the geometry far away. Distances are subtly altered. The rate at which time passes changes from place to place. The fabric of the universe itself is deformed by the presence of mass and energy. You've probably heard the analogy of a bowling ball on a stretched rubber sheet. Place a heavy ball on a taut sheet of rubber and the sheet sags, creating a curved depression around the ball. Roll a marble across the sheet and, instead of travelling in a straight line, the marble curves inward toward the bowling ball, following the dip in the surface. This analogy is far from perfect. It shows only 2-dimensional curvature, while spacetime is 4-dimensional. And it relies on an external gravity pulling the bowling ball down into the sheet, which is circular reasoning when you're trying to explain gravity itself. But the analogy captures one essential feature. The marble doesn't curve because the bowling ball reaches out and grabs it. The marble curves because the surface it moves on is curved. The bowling ball changed the geometry of the surface, and the marble responds to that changed geometry. This is the central insight of general relativity. Gravity is not a force acting between objects across empty space. Gravity is the curvature of spacetime caused by mass and energy. Objects don't get pulled by gravity. They follow the natural paths dictated by the shape of spacetime around them. When you see a planet orbiting a star, that planet is not being yanked around by an invisible rope. It is travelling along the straightest possible path available to it through curved spacetime. And in curved spacetime, the straightest possible path isn't what you would call a straight line in ordinary flat space. It's a curve, an orbit, because the space-time itself is curved. These straightest possible paths through curved spacetime have a technical name. They're called geodesics. A geodesic is the closest thing to a straight line that exists in curved geometry. On a flat surface, like a tabletop, a geodesic is simply what you'd expect: a straight line, the shortest distance between 2 points. But on a curved surface, geodesics become more interesting. Consider the surface of Earth. Earth is a sphere, and on a sphere, straight lines don't exist in the usual sense. The closest thing to a straight line on a sphere is a great circle, the largest possible circle you can draw on the surface. The equator is a great circle. Lines of longitude running from pole to pole are great circles. These are the geodesics of a spherical surface. They are the straightest, shortest paths you can follow while staying on the surface. This is why airlines fly routes that look curved on flat maps. If you plot a flight from New York to Tokyo on a flat wall map, the shortest looking route appears to be a straight line across the map, heading due west across the United States and the Pacific. But the actual shortest route goes far to the north, arcing up over Alaska. On the flat map, this looks like a long detour. But on a globe, you can stretch a string between New York and Tokyo and see that the northern arc is genuinely shorter. The flat map distorts the geometry. The globe reveals the truth. The airplane is following a geodesic, the shortest path on a curved surface. It looks curved on the map only because the map is flat and the surface is not. Here's another way to see it. Imagine two people standing on the equator a short distance apart, both facing due north. They start walking in perfectly straight lines, each following a line of longitude toward the North Pole. Neither one turns, neither one steers toward the other. They both walk in the straightest possible path on the curved surface. And yet, as they walk, they gradually converge. The distance between them shrinks. Eventually, they meet at the pole. If you didn't know Earth's surface was curved, you might conclude some invisible force was pulling them together. But there is no force. The surface is curved, and straight paths on a curved surface converge. That is gravity in a nutshell. Spacetime works the same way. Near a massive object like the Sun, spacetime is curved. Geodesics through that curved spacetime are not straight lines, they're curves. An orbit around the Sun is a geodesic. Earth doesn't orbit because a force keeps pulling it inward. Earth orbits because the straightest available path through the curved spacetime near the Sun happens to loop back around. Earth is doing the most natural thing possible. It's following the path of least resistance through curved geometry. It would take a force to stop it from orbiting, to push it off its geodesic, not to keep it on one. And here is the piece that solves our original paradox. Geodesics are determined by the geometry of spacetime, not by the mass of the thing following them. The shape of the path depends entirely on the curvature of spacetime, which is created by the massive object like the star or galaxy. It does not depend on whether the thing travelling along that path is heavy or light, fast or slow, massive or massless. A planet follows a geodesic. A speck of dust follows a geodesic. A rock, a spacecraft, a grain of pollen drifting through space, they all follow geodesics. And a massless photon, a particle of light with zero rest mass, also follows a geodesic. The path is already there, carved into the shape of spacetime itself. You don't need mass to follow a curved path through curved geometry. You just need to be moving through that geometry. And everything moves through spacetime, including light. Think of it like a road that curves around a mountainside. If you drive on that road, your car follows the curve. It doesn't matter whether your car is a heavy truck or a lightweight motorcycle. Both follow the same curve because the curve belongs to the road, not to the vehicle. The road's shape determines the path. The vehicle just follows it. In general relativity, spacetime is the road. Mass curves the road, and everything travelling on that road, massive objects and massless photons alike, follows the curves. A photon doesn't need mass to be affected by gravity, because gravity isn't pulling on the photon. The spacetime through which the photon travels is curved, and the photon faithfully follows that curvature. there is no force, there is no contact. There is no invisible hand reaching across empty space to grab the light and bend it. The light is moving through bent space and bent time, and its path bends accordingly. This is why the word force is deeply misleading when applied to general relativistic gravity. Newton described gravity as a force, an interaction between two masses pulling on each other across distance. Einstein says there is no force at all. What we call gravity is the geometry of spacetime. When you stand on Earth's surface, you feel weight pressing down through your body into your feet. In Newton's picture, that's gravity pulling you downward and the ground resisting. In Einstein's picture, something profoundly different is happening. You are being accelerated. The ground is pushing you upward, away from the geodesic you would naturally follow if nothing were in the way. If the ground vanished beneath your feet and you fell freely, you would feel weightless, no force, no acceleration. That free-fall path, the weightless path, is the geodesic. It is your natural trajectory through curved spacetime. You don't need a force to follow a geodesic. You need a force to deviate from one. The ground pushes you off your natural path, and you feel that push as weight. An astronaut orbiting Earth is following a geodesic. No force acts on her. She is weightless, in free fall, traveling along the straightest possible path through the curved spacetime around Earth. That path happens to loop back on itself, forming a closed orbit, because spacetime near Earth is curved strongly enough to bend geodesics into circles. Now apply this directly to light. A photon emitted by a distant star travels through spacetime. Far from any massive object, spacetime is approximately flat, and the photon's geodesic is approximately a straight line. But when the photon passes near something massive, spacetime in that region is curved. The geodesic curves. The photon follows the curved geodesic. Its path bends. No force was applied, no contact was made. The massive object never reached out and touched the photon. It didn't need to. The massive object curved the spacetime, and the photon travelled through that curved spacetime along the only kind of path available to it, a geodesic. The bending of the photon's path was not caused by a force acting on the photon. It was caused by the shape of the road the photon was travelling on. This is the fundamental difference between Newton's gravity and Einstein's gravity. Newton says gravity is a force that acts between objects with mass. If something has no mass, there is no force, and gravity has nothing to say. Einstein says gravity is the curvature of spacetime, caused by mass and energy, and everything moving through spacetime follows paths shaped by that curvature, whether the moving thing has mass or not. Newton needs mass for gravity to work. Einstein does not. Newton requires a target to pull on. Einstein requires nothing of the sort. The geometry does all the work. This is why gravity can change light without touching it, because gravity was never about touching. Gravity was never a hand grabbing objects and hauling them along. That was Newton's picture, and while it was a magnificent approximation that works beautifully for most everyday and astronomical purposes, it was not the deepest truth. Gravity is the shape of the universe itself. It is the curvature of spacetime. Light, like everything else, moves through spacetime. When spacetime is curved, light follows the curves. There is no hand, there is no rope, there is no contact, there is only geometry. Think about what this means for the question we started with. How can gravity change light without touching it? That question assumes gravity is something that needs to touch things to affect them. It assumes gravity is a force reaching out and making contact. Einstein showed that assumption is wrong. Gravity doesn't touch anything. Gravity is the shape of the stage, and everything, absolutely everything, performs on that stage. Massive planets, tiny dust grains, and massless beams of light. But Einstein's equations don't just tell us that light bends, they tell us how much it bends, and they give a very specific answer that differs from anything Newton's framework can produce. They also tell us that the curvature of spacetime does something else to light beyond bending its path. It changes its measured energy. And both of these predictions have been confirmed by observation in spectacular fashion. Einstein's general relativity didn't just say that gravity bends light, it said how much. And the number it predicted was very specific, very precise, and very different from what Newton's framework would give. We talked earlier about how Johann von Soldner, using Newtonian mechanics back in 1801, calculated that starlight grazing the edge of the sun should deflect by about 0.87 arcseconds. That was based on treating light as tiny particles with an effective mass and applying Newton's gravitational formula. Einstein, using general relativity, calculated the deflection to be 1.75 arcseconds. Exactly double. Not roughly double, not approximately double, precisely, mathematically double. And the reason for this doubling reveals something profound about how spacetime curvature actually works. In Einstein's picture, spacetime near a massive object like the Sun is curved in two distinct ways. Both space and time are warped. Consider them separately for a moment. The curvature of time near a massive object is what produces the gravitational acceleration we're all familiar with. When you drop a ball and watch it fall, that acceleration is caused by the warping of time near Earth's surface. Time runs slightly slower closer to the ground than it does higher up, and this difference in the rate of time creates the effect we experience as gravitational pull. This is the piece that Newton's gravity captures, even though Newton didn't know he was describing time curvature. His equations happen to match the time curvature component of general relativity quite well in most situations. But space itself is also curved near a massive object. Distances are slightly distorted. The straight paths through space are subtly bent. This spatial curvature is something Newton's theory doesn't account for at all. For slow-moving objects, like planets or falling apples, the spatial curvature is negligible compared to the time curvature. These objects move much, much slower than the speed of light, so they experience the time warping far more intensely than the space warping. Newton's gravity, which effectively captures only the time curvature, works beautifully for these cases. That's why Newtonian gravity is such a good approximation for most situations. For slow things, you only need half the picture, and Newton gives you that half with remarkable accuracy. Let me give you an analogy that makes this clearer. Imagine you're walking slowly through a city where the streets are built on slightly uneven ground. The ground dips a little to the left. If you're walking slowly, taking one step every second or two, that slight leftward slope barely affects you. You notice it. Maybe your path drifts a tiny bit to the left, but it's a minor effect. You're mostly moving forward through time, spending most of your journey just existing, taking one step, pausing, taking another. The unevenness of the ground, the spatial curvature, is something you barely interact with because you're moving through space so slowly. Now imagine someone sprinting through the same city at enormous speed. They're covering ground rapidly, interacting with every bump and slope in the terrain far more intensely than you are. That same leftward dip that barely nudged your path sends the sprinter veering significantly. They're moving through space fast enough that every feature of the ground's shape matters. This is roughly the situation with light. A slowly orbiting planet is the walker. It spends most of its existence moving through time, not space, so it mainly feels the time curvature. Light is the ultimate sprinter. It moves through space at the maximum possible speed. It interacts with the spatial curvature just as intensely as it interacts with the time curvature. both contribute equally to bending its path. And that's why the total bending is double what Newton would predict. Newton's framework only accounts for the timepiece. Einstein accounts for both. The prediction is precise. 1.75 arcseconds of deflection for starlight grazing the edge of the Sun, exactly double the 0.87 arcseconds that Newton's framework produces. This factor of 2 is not a small correction or a rounding difference. It is a fundamental distinction between two entirely different theories of gravity. Newton says light bends by a certain amount because gravity pulls on its effective mass. Einstein says light bends by twice that amount because space-time itself is curved in two ways that are equally important for anything travelling at the speed of light.
The two theories make cleanly different predictions. One of them must be right and the other wrong. All you needed was a measurement. Now measuring 1.75 arcseconds is extraordinarily difficult. It is a minuscule angle. If you held a single human hair at arm's length, it would cover an angle of roughly 60 arcseconds. 1.75 arcseconds is more than 30 times smaller than that. You're looking for a shift in a star's apparent position that is vanishingly tiny. And there's a practical problem. To see how much gravity bends starlight near the Sun, you need to observe stars that appear close to the Sun in the sky. But normally, you can't see stars near the Sun because the Sun is overwhelmingly bright. Its glare washes out everything nearby. You need a way to block the Sun's light so you can see the stars behind it. Nature provides exactly one way to do this: a total solar eclipse. During totality, when the Moon passes directly in front of the Sun and blocks its disk completely, the sky goes dark and stars become visible even right next to the Sun's position. You can photograph those stars and measure their positions with precision. Then, months later, you photograph those same stars at night when the Sun is nowhere near them and compare. If the stars near the Sun's position during the eclipse appear slightly shifted outward compared to their normal positions, that shift is caused by the Sun's gravity bending their light. Einstein published his general relativity field equations in late 1915. He calculated the predicted deflection of 1.75 arcseconds and published a detailed paper on it in 1916. But the world was in the middle of the First World War, and scientific expeditions to observe solar eclipses were not exactly a priority. The next total solar eclipse wouldn't cross observable territory until May of 1919, and by then the war had ended. Arthur Eddington, a British astronomer and one of the few scientists in Britain who had carefully studied Einstein's new theory, organised two expeditions to observe the 1919 eclipse. One team travelled to Sobral in northern Brazil. The other, led by Eddington himself, travelled to the island of Principe off the west coast of Africa. Both locations lay along the path of totality, where the eclipse would be total and the sky would darken enough to photograph stars near the Sun. The expeditions were tense. Weather threatened both sites. Clouds covered the sky at Principe for most of the morning, and Eddington worried that the entire journey might be wasted. But the sky partially cleared just before totality, and both teams managed to capture photographs. When the photographic plates were developed and the star positions carefully measured, the results were clear. The stars near the Sun's edge had shifted outward in their apparent positions, and the amount of that shift was consistent with Einstein's prediction of 1.75 arcseconds. It was not consistent with the Newtonian prediction of 0.87 arcseconds. The observed bending was roughly twice what Newton's framework would produce. General relativity had passed its first major observational test. Gravity bends light not because it pulls on light's mass, but because it curves the space-time through which light travels. And the amount of bending, the factor of 2, confirmed that both space and time contribute equally to the curvature experienced by anything moving at the speed of light. The results made Einstein a worldwide celebrity almost overnight. Newspapers ran headlines about the revolution in physics. A new theory of gravity had been confirmed by direct observation. The universe worked differently from what we had believed for over 2 centuries. It's worth pausing to appreciate what actually happened during those few months in 1919, because the human story is as extraordinary as the physics. Einstein had published his prediction during a world war. He was a German scientist. Eddington was British. The two nations had been locked in one of the most devastating conflicts in human history. Millions of soldiers had died. Scientific cooperation across enemy lines had essentially ceased. And yet, Eddington, a Quaker and a pacifist who had narrowly avoided prison for refusing military service, chose to mount an expensive, logistically difficult expedition to test the theory of a scientist from the country his own nation had been fighting. The Astronomer Royal of Britain, Frank Dyson, had helped plan the expedition and argued that its scientific importance transcended national boundaries. This was not a popular position at the time. The wounds of the war were still fresh. Many people in Britain and across Europe had no interest in validating the work of a German physicist. But Dyson and Eddington pressed forward, arguing that the eclipse of 1919 offered a rare opportunity. The Sun would be positioned in front of a particularly bright cluster of stars, making the measurement easier than it would be during most eclipses. If they missed this chance, they might wait years or decades for another opportunity as favourable. The Sobral team in Brazil had better weather and captured clearer photographs. The Principe team, led by Eddington, struggled with clouds and captured fewer usable plates. But when the measurements were analysed, both sets of data pointed to the same conclusion. The deflection was consistent with Einstein's prediction of 1.75 arc-seconds, not Newton's 0.87. On November 6, 1919, the results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The room was packed. The portrait of Isaac Newton looked down from the wall as the speakers presented evidence that Newton's theory of gravity was incomplete. J.J. Thomson, the president of the Royal Society and the discoverer of the electron, called general relativity one of the greatest achievements in the history of human thought. The next morning, newspapers around the world carried the story. The London Times headline read, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Einstein, who had been quietly confident in his theory for years, reportedly reacted to the news with characteristic calm. When asked what he would have thought if the observations had contradicted his prediction, he is said to have replied that he would have felt sorry for the Lord because the theory was correct. Whether the quote is perfectly accurate or slightly embellished by history, it captures something real about Einstein's relationship with general relativity. He believed in it not because he hoped it was right, but because the mathematics was too beautiful and too logically coherent to be wrong. The eclipse results confirmed what the equations already demanded, but the 1919 measurements, while historic, were not terribly precise. The error bars were large. Some critics argued the data was ambiguous, that Eddington had cherry-picked his best results and discarded plates that were less favourable. These criticisms had some validity. The early measurements were rough by modern standards. It took decades of additional observations, better instruments, and eventually radio telescopes capable of measuring the deflection of radio waves from distant quasars to confirm the 1.75 arc-second prediction with high precision. Today, the deflection of light by the Sun has been measured to an accuracy of better than 1 part in 10,000, and it matches Einstein's prediction exactly. There is no remaining ambiguity. General relativity is correct on this point, and Newton's prediction is exactly half the observed value. But the bending of starlight near the Sun
was just the beginning of the story.
Because when you follow the implications of space-time curvature to their logical conclusion, you discover something far more dramatic than a tiny shift in a star's apparent position. You discover gravitational lensing. Here's how it works. Imagine a galaxy very far behind a massive object like another galaxy or a cluster of galaxies. Light from that distant background galaxy travels toward us across billions of light years. Along the way, it passes near the massive foreground object. The space-time around that foreground object is curved. The light follows the curvature of space-time, and its path bends as it passes by. If the alignment is right, light that would normally miss us entirely, light traveling in a direction that would take it past us and off into empty space, gets bent back toward us by the curved space-time around the foreground object. We see that light. We see the distant galaxy. And we see it in a position that isn't where the galaxy actually is, because the light took a bent path to reach us. The massive foreground object is acting like a lens. Not a glass lens that refracts light through a transparent medium, but a gravitational lens that bends light by curving space-time itself. The physics is completely different from optical refraction, but the net effect is similar. Light from a distant source is redirected by an intervening object, and the image of the distant source appears distorted, magnified, or multiplied. And this is critical. The light does not slow down. This is fundamentally different from what happens in a glass lens. When light enters glass or water, it actually slows down inside the medium, and that change in speed is what causes it to refract, to bend at the surface. But gravitational lensing does not work this way. The photon is not passing through a medium. It is not being slowed by anything. In every local patch of space it passes through, it is moving at exactly 300,000 kilometers per second, the full speed of light. Locally, at every point along its journey, the photon is traveling in a straight line at full speed. But the space-time through which it travels is curved, so that locally straight path through curved geometry becomes a globally bent path when viewed from far away. The distinction matters enormously. Gravity is not friction. It does not drag on light or resist its motion or sap its speed. It reshapes the road, not the traveller. The photon sails along at full speed on a bent road, and because the road is bent, the photon ends up somewhere different from where it would have arrived on a straight road. The road is bent because space-time is curved. The space-time is curved because mass and energy are present. That's the entire mechanism. Einstein himself explored the idea of gravitational lensing in a brief paper in 1936, although he was somewhat dismissive of the practical possibilities. He calculated that if a distant star happened to be precisely aligned behind a closer foreground star, as seen from Earth, the foreground star's gravity would bend the background star's light into a ring, a perfect circle of light centered on the foreground star. He worked out the mathematics and showed the ring would form, but he concluded that such perfect alignments would be exceedingly rare, and the resulting rings too small to observe. He noted, almost as an aside, that there was no great chance of observing this phenomenon. He was right about the difficulty of star-to-star lensing. Individual stars generally don't have enough mass to produce detectable lensing effects at interstellar distances, and the perfect alignments required are indeed extremely rare. But Einstein was thinking too small. He was considering individual stars. He wasn't considering galaxies and galaxy clusters, objects with trillions of times more mass than a single star. In 1937, just a year after Einstein's paper, the Swiss-American astronomer Fritz Zwicky pointed out that galaxies and clusters of galaxies could act as gravitational lenses. Their enormous mass would create much stronger lensing effects over much larger scales, and the probability of the right alignment was much higher, because galaxies are large and there are many of them.
Zwicky predicted that gravitational lensing by galaxy clusters would be observable and would become a valuable tool for astronomy. He was ahead of his time by decades, but he was absolutely right. The first confirmed case of gravitational lensing came in 1979, when astronomers discovered what appeared to be two nearly identical quasars sitting very close together in the sky. Quasars are extraordinarily luminous objects at the centers of distant galaxies, powered by supermassive black holes consuming enormous amounts of material. These two quasars had nearly identical spectra, the same pattern of light absorption and emission at the same wavelengths. They had the same redshift, meaning they were at the same distance. They were too similar to be two separate objects. The explanation was gravitational lensing. There was one quasar far in the background, and a massive galaxy sitting between it and us. The galaxy's gravity curved spacetime around it, bending the quasar's light along two different paths around the galaxy, each path arriving at Earth from a slightly different direction. We saw two images of the same quasar, a cosmic mirage created by the curvature of spacetime. This discovery, known as the twin quasar, confirmed that gravitational lensing by galaxies is real and observable, just as Zwicky had predicted over 40 years earlier. Since then, gravitational lensing has become one of the most powerful tools in modern astronomy, and the range of effects it produces is extraordinary. When the alignment between a distant source, a foreground mass, and the observer is nearly perfect, you can get the ring that Einstein predicted. These Einstein rings are circles or near circles of light, the image of the distant source smeared into an arc or a complete ring by the lensing effect. Perfect rings are rare because perfect alignment is rare, but partial rings and dramatic arcs are common. The Hubble Space Telescope and the James Webb Space Telescope have captured stunning images of these arcs, thin, luminous curves of light stretching around massive galaxy clusters, each arc the distorted image of a galaxy far behind the cluster whose light has been bent and stretched by curved spacetime. Some of the most spectacular examples come from massive galaxy clusters. Able 2218, a galaxy cluster about 2.3 billion light-years from Earth, produces dozens of arcs and multiple images of background galaxies. Every single one of those arcs is the light of a real galaxy, a galaxy that sits far behind the cluster, whose light has been bent around the cluster by spacetime curvature. Some of those background galaxies appear as multiple images, the same galaxy visible in 2 or 3 or even 5 different positions around the cluster, each image showing light that travelled a different bent path around the cluster to reach us. Able 370 produces one of the most dramatic gravitational lensing images ever captured. A long, thin arc of light stretches across the cluster, nicknamed the Dragon by astronomers. That arc is the stretched, smeared image of a single galaxy far behind the cluster. Its light has been caught by the curved spacetime around Able 370 and drawn out into this enormous luminous strand. The galaxy itself is far away and would ordinarily be too faint to see, but the gravitational lens has magnified it, collecting light that would have spread out in all directions and focusing some of it toward us. The lens makes the invisible visible, and that magnification effect is one of the most valuable features of gravitational lensing. Massive galaxy clusters act as natural telescopes, magnifying the light of galaxies far behind them. Galaxies that are too distant and too faint to see with even our most powerful telescopes become visible when a gravitational lens magnifies them. The James Webb Space Telescope has used gravitational lensing to observe some of the most distant galaxies ever detected, galaxies whose light left them when the universe was less than 1 billion years old. Without the lensing magnification, those galaxies would be invisible, lost in the darkness of extreme distance. The curvature of spacetime, the same phenomenon that tells us gravity changes light without touching it, gives us a window into the earliest epochs of cosmic history. But gravitational lensing does something even more remarkable than magnifying distant objects. It reveals mass that we cannot see in any other way. The amount of lensing, how much the light bends, how many arcs form, how distorted the images become, depends on how much mass is doing the curving. More mass means more space-time curvature, which means more bending, which means stronger lensing effects. By carefully measuring the lensing, you can calculate how much mass is responsible. You can weigh the lens. When astronomers did this for galaxy clusters, they discovered something startling. The lensing effects were far too strong to be explained by the visible matter alone. The galaxies you can see in the cluster, all the stars, gas, and dust that emit or absorb light, don't have nearly enough mass to produce the observed lensing. Something else is there. Something with mass that curves spacetime and bends light, but doesn't emit any light of its own. Something invisible. This is dark matter. And gravitational lensing is one of the strongest pieces of evidence that it exists. Dark matter doesn't interact with light. It doesn't emit photons. It doesn't absorb photons. It doesn't glow. It doesn't cast shadows. You cannot see it with any telescope at any wavelength. But it has mass, and mass curves spacetime. And curved spacetime bends light. So dark matter reveals itself through gravitational lensing, through the effect it has on the paths of photons that pass through the spacetime it curves. One of the most dramatic demonstrations of this is the Bullet cluster, a pair of galaxy clusters that collided and passed through each other roughly 150 million years ago. During the collision, the hot gas in each cluster, which makes up most of the visible mass, slammed together and slowed down, piling up in the middle like two clouds of steam colliding in slow motion. But the galaxies themselves, which are much smaller and more widely spaced than the gas, passed right through each other without interacting much, continuing on to the far side of the collision. Now, if the visible gas were the main source of mass, the gravitational lensing should be strongest where the gas is, in the middle of the collision. But that's not what observations show. The lensing is strongest on the two outer sides, where the galaxies ended up after passing through each other. Something with a lot of mass passed right through the collision without interacting with the gas. That something is dark matter. It has mass, so it curves spacetime and produces lensing. But it doesn't interact with normal matter or light, so it slid right through the collision like a ghost, carrying its gravitational influence to the far side. This is space-time curvature, making the invisible visible. Dark matter curves space-time. The curved space-time bends the paths of photons passing through it. We detect those bent paths as gravitational lensing. And by mapping the lensing, we can map where the dark matter is, even though we cannot see it directly. The universe is using light, massless light, to reveal the presence of mass that produces no light of its own. The mechanism that makes this possible is exactly the mechanism we've been discussing all along. Space-time curvature bends the paths of photons without any physical contact, without any force, without touching the light at all. There is also a subtler form of lensing called weak lensing that doesn't produce dramatic arcs or multiple images. Instead, it causes tiny, systematic distortions in the shapes of background galaxies. Each galaxy is distorted by a minuscule amount, so small that for any individual galaxy, you couldn't tell anything was happening. But when you analyze thousands or millions of background galaxies statistically, the pattern of those tiny distortions reveals the distribution of mass in the foreground, including dark matter. It's like looking at a field of tall grass, and noticing that the stalks are all leaning slightly in the same direction. Any single stalk might lean that way by chance, but when millions of stalks all lean the same way, you know there's a breeze, even if you can't feel it yourself. Weak lensing is the breeze in the tall grass of distant galaxies, and the wind creating it is the curvature of spacetime. Today, weak lensing surveys map the distribution of dark matter across enormous volumes of the universe. These maps reveal a cosmic web of dark matter filaments stretching across billions of light-years, with galaxies clustering along the filaments and vast empty voids between them. All of this structure is revealed through the effect of space-time curvature on photons, massless particles having their paths subtly bent by mass they never touch and never interact with in any way except through the geometry of the space-time they travel through. Every one of these observations, the bending of starlight by the Sun confirmed in 1919, the twin quasar discovered in 1979, the spectacular arcs around galaxy clusters, the Einstein rings, the mapping of dark matter through weak lensing, every single one is a confirmation of the same underlying truth. Gravity changes light without touching it, because gravity is not a force that touches things. Gravity is the curvature of spacetime. Photons follow paths through that curved spacetime. Their paths bend. Multiple images form. Distant galaxies get magnified. Dark matter reveals itself. And throughout all of it, no force was exerted on any photon. No contact was made. The light was never pushed, pulled, grabbed, or slowed. It travelled at full speed along the curved geometry of spacetime, and the curvature did everything. The paths that light follows through curved spacetime have a specific technical name. They are called null geodesics. Earlier, we talked about geodesics in general, the straightest possible paths through curved geometry. Massive objects follow what are called time-like geodesics, paths where space-time intervals are positive, paths that experience the passage of time. Light follows a different kind of geodesic. For a photon, the space-time interval along its path is exactly zero. It is null. This is a deep consequence of travelling at exactly the speed of light. In flat spacetime, the spacetime interval between two events is calculated using the difference in their spatial separation and their time separation. For light, these two contributions cancel exactly, giving an interval of zero. In curved spacetime, null geodesics are the paths where this zero interval is maintained everywhere along the path. The photon travels through curved geometry, and at every point along its journey, the space-time interval is zero. The curvature of spacetime shapes these null geodesics, bending them, curving them around massive objects, sometimes wrapping them into arcs or rings. But the photon is always following the straightest possible path available to it in the curved geometry. It is not being deflected by a force. It is following the natural geometry of the universe. Curved geometry produces curved paths, and for light, those curved paths are null geodesics, the paths of zero interval through warped spacetime. This is why light does not slow down when it passes through a gravitational field. A force acting on an object changes the object's speed or direction. If gravity were a force acting on photons, you might expect it to slow them down or speed them up. But gravity is not a force, it is geometry. The photon's local speed is always exactly the speed of light in every patch of spacetime it passes through. The speed does not change. What changes is the path. The road curves, but the traveller does not slow down. The photon enters the curved region at the speed of light, traverses it at the speed of light, and exits it at the speed of light. At no point during the journey does the photon travel at anything other than 300,000 kilometers per second relative to the local spacetime it passes through. This distinction is critical. gravity does not act like friction on light. It does not resist light's motion. It does not extract energy from the photon through contact or drag. The mechanism is purely geometric. The mass of a star or galaxy warps the spacetime around it. Light enters that warped spacetime and follows the curvature. Its path bends, and it emerges on the other side, still traveling at the speed of light, having followed the natural shape of the universe without any force ever having been applied to it. And yet, while gravity does not change the speed of light, it does change something else. Something equally important and equally strange. The measured energy of a photon can change as it travels through curved spacetime. And this energy shift, like the bending of light's path, happens without any contact, without any force, and without anything physically touching the photon at all. Gravity doesn't just bend the path of light, it does something else to light, something equally strange, equally measurable, and equally impossible to explain within Newton's framework. Gravity changes the measured energy of a photon, not by touching it, not by slowing it down, not by applying friction or drag or any kind of contact, but by warping time itself. This effect is called gravitational redshift, and understanding it requires confronting one of the most disorienting consequences of general relativity. Time does not tick at the same rate everywhere. In Newton's universe, time was absolute. 1 second was 1 second everywhere, always, for everyone. Whether you were standing at sea level or on top of a mountain, whether you were near a star or floating in empty space a billion light years from the nearest galaxy, time moved at the same steady rate. A clock is a clock is a clock. This was so deeply intuitive that nobody questioned it for over 2 centuries. Einstein shattered this assumption. General relativity tells us that the rate at which time passes depends on the gravitational field you're in. Specifically, time runs slower in stronger gravitational fields. A clock at the base of a mountain ticks slightly slower than an identical clock at the summit. A clock on the floor of your house ticks slightly slower than a clock on the roof. A clock on Earth's surface ticks slightly slower than a clock in orbit far above. These differences are real. They are not caused by the clocks being faulty or by measurement errors. Time itself passes at different rates at different locations in a gravitational field. 2 perfectly identical atomic clocks, manufactured side by side, synchronized to the same moment, will drift apart if you place one closer to a massive object and one farther away. The lower clock, deeper in the gravitational field, accumulates fewer ticks. It doesn't malfunction, it keeps perfect time. But the time it keeps is genuinely slower than the time experienced higher up. This is gravitational time dilation, and it is one of the most precisely confirmed predictions in all of physics.
Now, what does this have to do with light?
Consider a photon emitted from the surface of a star. At the surface, deep in the star's gravitational field, time runs slightly slower than it does far away from the star. The photon is a specific color when it is emitted, which means it has a specific wavelength and a specific frequency. That frequency is tied to the oscillation of the electromagnetic field, and that oscillation is governed by the rate at which time passes at the emission point. The photon climbs away from the star, moving outward through the gravitational field toward a distant observer. As it climbs, it moves into regions where time runs faster. The photon itself doesn't slow down. It travels at the speed of light, 300,000 kilometers per second, at every point along its journey. Nothing changes about the photon's local behavior, but when the distant observer, sitting in a region where time ticks faster, receives the photon and measures its frequency, something has changed. The photon was born in a region of slow time. Its frequency was set by the rate of time at the surface of the star. But the distant observer lives in a region of faster time. From the observer's perspective, the photon's oscillations appear stretched out. the frequency is lower than it was at the moment of emission. Lower frequency means longer wavelength, and in visible light, longer wavelength means redder color. This is gravitational redshift. The photon's measured wavelength has stretched, its measured frequency has dropped, its measured energy has decreased because a photon's energy is directly proportional to its frequency. A lower frequency photon carries less energy. The photon that left the star as blue light might arrive at the distant observer as green light, or yellow light, or even red light, depending on how strong the gravitational field is and how far the photon had to climb. And here is the critical thing to understand. Nothing took energy from the photon. No force drained it. No friction slowed it. No hand reached out and pulled energy away. The photon did not bump into anything, interact with anything, or lose energy to any physical process. It traveled through empty space-time at the speed of light, untouched and undisturbed. The change in its measured energy is entirely because time runs at different rates at different locations in the gravitational field. The photon's frequency was set by slow time at the bottom. The observer's measurement is made in fast time at the top. The mismatch between those two rates of time is what produces the redshift. Think of it this way. Imagine you are standing at the top of a tall cliff, and someone at the bottom is throwing a ball upward once every second according to their clock. You catch the balls at the top, but time at the bottom runs slightly slower than time at the top, so their seconds are slightly longer than your seconds. From your perspective at the top, the balls arrive at intervals slightly longer than 1 second by your clock. The rhythm is stretched. The frequency of arriving balls is lower. Nothing happened to the balls in transit. They didn't slow down. They didn't lose anything. The difference is entirely due to the clocks ticking at different rates at the two locations. Gravitational redshift works the same way. The photon is the ball. The frequency is the rhythm. The gravitational field creates a difference in the rate of time between the emission point and the observation point. The photon carries the rhythm of the slower clock into the region of the faster clock, and the mismatch shows up as a lower frequency, a longer wavelength, a shift toward the red end of the spectrum. The reverse effect also exists. If a photon falls into a gravitational field, moving from a region of faster time to a region of slower time, its measured frequency increases, its wavelength shortens, its measured energy goes up. This is gravitational blue shift. A photon falling toward a massive object arrives with more energy than it had when it started, not because something pushed it or accelerated it, but because it moves from a region where time runs faster into a region where time runs slower, and the mismatch compresses its rhythm. Einstein predicted gravitational redshift as part of general relativity in 1915 and 1916. He recognized it was a direct consequence of the curvature of spacetime, specifically the curvature of time near massive objects. But measuring the effect turned out to be extraordinarily difficult. The gravitational redshift caused by Earth's gravity is incredibly tiny. For a photon climbing from Earth's surface up to a satellite in orbit, the fractional change in frequency is roughly 1 part in a billion. Measuring something that small requires phenomenally precise instruments. The first clean, direct measurement of gravitational redshift came in 1959 in a brilliant experiment by two physicists at Harvard named Robert Pound and Rebka. Their experiment, now known as the Pound-Rebka experiment, is one of the most elegant tests of general relativity ever performed, and they did it inside a single building. Pound-Rebka used a technique involving gamma rays emitted by radioactive iron atoms. These gamma rays have an extremely precise frequency, like a tuning fork that hums at one exact pitch. The physicists placed a gamma ray source at the bottom of Jefferson Tower at Harvard, a tower about 22.6 meters tall. At the top, they placed a detector made of the same type of iron atoms. The idea was simple.
If general relativity is correct, the gamma rays emitted at the bottom of the tower should be very slightly redshifted by the time they reach the top, because time runs slower at the bottom, closer to Earth's center, than at the top. The fractional change in frequency over 22.6 meters of height in Earth's gravitational field is absurdly small, about 2.5 parts in 10 to the 15th power. That means the frequency changes by roughly 0.000000000000025%. To detect a shift that tiny, you need instruments of almost unbelievable precision. Pound-Rebka had such precision. The technique they used, called Mossbauer spectroscopy, allowed them to measure changes in gamma-ray frequency with extraordinary sensitivity. The iron atoms in the detector at the top would only absorb the incoming gamma rays if those gamma rays had exactly the right frequency. If the frequency was even slightly off, the absorption would drop. By carefully comparing the absorption rate with and without the expected gravitational redshift, they could detect whether the frequency had shifted during the 22.6 meter climb. It had. The measured shift matched Einstein's prediction to within about 10% accuracy. Later refinements of the experiment improved the precision to about 1%. A gamma ray climbing less than 23 meters in Earth's gravitational field, a distance shorter than the length of a swimming pool, experienced a measurable redshift caused by the difference in the rate of time between the bottom and the top of a university building. No force touched those gamma rays. No friction slowed them. Nothing drained their energy. They traveled at the speed of light from the bottom of a tower to the top through less than 23 meters of air. And they arrived with a measurably lower frequency than they had when they left. The only explanation is that time itself runs at different rates at the bottom and the top, and the photon's measured frequency reflects that difference. Spacetime curvature, the warping of time by Earth's mass, changed the measured energy of light without any physical contact whatsoever. In 1971, two physicists named Hafele and Keating performed an even more dramatic test. They flew cesium atomic clocks on commercial airliners around the world, once heading eastward and once heading westward, then compared the airborne clocks with identical clocks that stayed on the ground. The results confirmed both effects predicted by relativity. The moving clocks ticked at different rates due to their speed, the special relativistic time dilation, and also due to their altitude, the gravitational time dilation from general relativity. The clocks that flew at higher altitude ticked slightly faster than the ground clocks, gaining a few hundred nanoseconds over the course of the flights. The differences were tiny, but measurable, and matched Einstein's predictions precisely. In 1976, an experiment called Gravity Probe A launched a hydrogen maser clock on a rocket to an altitude of about 10,000 kilometers. The clock in space ticked faster than identical clocks on the ground, exactly as general relativity predicts. The measurement confirmed gravitational time dilation to an accuracy of about 70 parts per million, a spectacular confirmation of Einstein's theory. But you don't need rocket launches or gamma-ray experiments to see the practical effects of gravitational time dilation. You use it every day without realizing it. Every time you check a map on your phone, every time you use navigation to drive somewhere, every time a delivery app tells you your food is 5 minutes away, you are relying on a system that would fail completely if it didn't account for the fact that gravity makes time run at different rates at different altitudes. GPS, the global positioning system, depends on signals from a constellation of satellites orbiting about 20,200 kilometers above Earth's surface. Each satellite carries extremely precise atomic clocks. Your phone receives signals from multiple satellites,
compares the arrival times, and uses the tiny differences to calculate your position. The accuracy of this system depends entirely on the clocks being synchronized. If the satellite clocks drift even slightly, the position calculation produces errors. A clock error of just 1 microsecond, 1/1,000,000th of a second, translates to a position error of about 300 meters. General relativity predicts that the clocks on GPS satellites, orbiting high above Earth where gravity is weaker, should tick faster than clocks on the ground. The difference is about 45 microseconds per day. That doesn't sound like much. But if GPS engineers didn't correct for this, the position errors would accumulate at a rate of more than 13 kilometers per day. Within a single day, your GPS would be off by more than 13 kilometers. Within a week, it would be off by more than 90 kilometers. The system would be useless. So GPS satellite clocks are deliberately adjusted before launch. Their tick rate is set slightly slower than ground clocks, so that once they're in orbit, where time runs faster due to weaker gravity, the effective rate matches the ground clocks. This correction is built into the system from the ground up, baked into the hardware. Every time your phone tells you where you are within a few meters, that accuracy is possible because engineers accounted for the fact that time runs at different rates at different heights in a gravitational field, exactly as Einstein predicted in 1915. This is gravitational time dilation, not as an abstract theoretical curiosity, but as an engineering necessity. The warping of time by mass is real, measurable, and consequential, and its effect on light, the gravitational redshift, is a direct, observable manifestation of that warping. There is yet another way spacetime curvature affects light that reinforces the same lesson. It is called the Shapiro time delay, and it was predicted in 1964 by the physicist Erwin Shapiro.
Here is the idea. Send a radar signal from Earth toward a planet on the far side of the Sun. The signal travels outward, passes close to the Sun, reaches the planet, bounces off, and returns along a similar path. Measure how long the round trip takes. According to flat spacetime, you can calculate the expected travel time based on the distances involved and the speed of light. But Shapiro predicted that the actual travel time would be slightly longer than this calculation suggests. The signal would arrive back a tiny bit late. Why? Not because the signal slowed down. The signal travels at the speed of light at every point along its path. Locally, in every small patch of space-time it passes through, it moves at exactly 300,000 kilometers per second. It does not decelerate as it approaches the Sun and accelerate as it moves away. Its local speed is constant, always, everywhere. The delay occurs because the space-time near the Sun is curved, and the path through curved space-time is longer than the path would be through flat space-time. The geometry itself is stretched. Distances near the Sun are slightly greater than they appear in a flat space calculation. It's as if the region of space-time around the Sun is slightly deeper or more extensive than you'd expect, and the signal has to traverse that extra geometry. The signal moves at the speed of light the whole time, but it has more space-time to cross. Shapiro predicted this effect in 1964 and proposed testing it by bouncing radar signals off Mercury and Venus when those planets were positioned behind the Sun as seen from Earth. The first measurements came in 1966 and 1967. The delays were detected, and they matched Einstein's predictions. The round-trip signals were delayed by about 200 microseconds when passing closest to the Sun, exactly the amount general relativity predicted. Those early radar measurements were groundbreaking,
but they were also limited in precision. Radar signals bounced off planets are messy. The planet's surface is rough, the signal scatters, and the returned echo is weak and noisy. Getting precise round-trip timing from such signals requires careful analysis and is subject to various sources of error. But the basic result was clear. The signals were delayed, and the delay was consistent with general relativity. The quest for better precision drove scientists to find cleaner experiments. Instead of bouncing signals off rocky planetary surfaces, they realized they could use spacecraft with onboard radio transponders. A transponder receives a signal and sends back a clean, strong reply at a known frequency. This eliminates the messiness of planetary surface reflections entirely. The signal goes up to the spacecraft, gets cleanly retransmitted, and comes back. The round-trip timing can be measured with extraordinary accuracy. More precise confirmations followed. In 2003, the Cassini spacecraft provided one of the most accurate tests of the Shapiro delay ever performed. While Cassini was orbiting Saturn, scientists used its radio transponder to send signals that passed close to the Sun. The measured delay matched general relativity's prediction to an accuracy of about 2 parts in 100,000. The agreement is extraordinary. Think about what that level of precision means. General relativity, a theory written down by one man working largely alone with pencil and paper over a century ago, predicts the travel time of a radio signal passing near the Sun to an accuracy of 2 parts in 100,000. That's like predicting the length of a road trip across an entire continent and being off by less than the length of a car. The theory doesn't just work. It works with a precision that borders on the absurd, and every one of these measurements, from the crude radar bounces of the 1960s to the exquisite Cassini data of 2002 and 2003, confirms the same thing. Spacetime near a massive object is curved. That curvature adds real, physical distance to any path that passes through it. Light crosses that extra distance at its usual speed, and the result is a measurable delay. The signal isn't slowed, the road is longer. The Shapiro delay confirms the same underlying truth from yet another angle. Spacetime near a massive object is curved, and that curvature affects the paths and travel times of light. The signal doesn't slow down. It doesn't get grabbed or dragged. It travels through curved geometry. And curved geometry means longer paths, which means longer travel times. Once again, no contact, no force, no friction, just geometry. Now, let's step back and see the complete picture we've built. We started with a paradox. Gravity is supposed to act on things with mass. Light has no rest mass, so gravity should have nothing to say to light. Photons should fly through the universe in perfectly straight lines, completely indifferent to whatever massive objects happen to be nearby. That is what Newton's framework demands. And it is demonstrably, observationally, experimentally wrong. General relativity resolves this paradox by revealing that gravity was never what Newton thought it was. Gravity is not a force pulling on mass across empty space. Gravity is the curvature of spacetime, the four-dimensional fabric of the universe, caused by the presence of mass and energy. Everything that moves through spacetime follows the geometry of spacetime. Massive planets follow curved paths called geodesics. Tiny dust particles follow geodesics. And massless photons follow null geodesics, paths of zero spacetime interval through curved geometry. The curvature of spacetime doesn't care whether the thing travelling through it has mass or not. The geometry is the geometry. Everything follows it. This is why gravity can bend light's path without touching it. The photon is not being pulled. It is not being pushed. It is traveling through space-time that happens to be curved by nearby mass. Its path curves because the road curves, not because someone grabbed the steering wheel. The photon moves at the speed of light in every local patch of space it passes through. It never slows down. It never speeds up. But its trajectory, viewed from far away, traces a curve because the space-time it traverses is warped. This is why gravity can change light's measured energy without friction. The photon climbing out of a gravitational field does not lose energy to any force or process. Nothing drains it, nothing resists it. The energy shift happens because time itself runs at different rates at different locations in the gravitational field. The photon carries the imprint of the time rate at its point of origin. When a distant observer in a region of faster time measures that photon, its frequency appears lower, its wavelength appears longer, its energy appears reduced. The photon didn't change, the clock changed. The framework of time through which the measurement is made differs from the framework in which the photon was born. This is why signals passing near massive objects arrive later than expected. The signal doesn't slow down. It crosses curved spacetime at the speed of light. But curved spacetime contains more distance than flat spacetime would. The geometry is stretched. The path is longer. And a longer path at the same speed means a longer travel time. Once again, no force, no friction, no contact. Just geometry. Every one of these effects, the bending, the redshift, the time delay, is a manifestation of the same single phenomenon: space-time curvature. The geometry of the universe is shaped by mass and energy. Light moves through that geometry. The geometry determines everything: the path the light follows, the energy an observer measures, the time it takes to arrive. All of it flows from the shape of space-time, and none of it requires gravity to touch, grab, push, or pull the light in any way. The distinction between Newton and Einstein is not just a matter of precision, not just a correction factor that makes calculations slightly more accurate. It is a fundamentally different understanding of what gravity is. Newton says gravity is a force between objects with mass. Einstein says gravity is the shape of the universe. Newton says you need mass for gravity to work on you. Einstein says you just need to exist in space-time, and space-time is all there is. Newton needs contact of a sort, a force transmitted between masses. Einstein needs no contact at all. The geometry is the interaction. And when you understand this, the original question dissolves. How can gravity change light without touching it? It dissolves because the question assumes gravity is the kind of thing that needs to touch. It assumes gravity is a force, a push, a pull, a hand reaching out across space. Remove that assumption and the paradox vanishes. Gravity doesn't touch light. Gravity doesn't touch anything. Gravity is the curvature of space-time, and light, like everything else in the universe, travels through space-time. Where space-time curves, paths curve. Where time warps, frequencies shift. Where geometry stretches, travel times grow. No contact required, no force needed, no mystery once you accept what gravity actually is. This is one of the most profound lessons in all of physics. For over 2 centuries, we thought gravity was a force, like a very long, invisible arm reaching across space and pulling on things. Einstein showed us that picture was wrong. Gravity is something deeper, something stranger, something more beautiful. It is the shape of reality itself. And light, the fastest thing in the universe, the one thing that has no mass at all, reveals this truth more clearly than anything else. Because if gravity can change the path and energy of something with zero mass, something it never touches, something it never makes contact with in any physical sense, then gravity was never about touching in the first place. It was always about geometry. It was always about the shape of the universe. There is something deeply humbling about this realization. For most of human history, we thought we understood what gravity was. It was the most obvious force in nature. You drop something and it falls. The ground pulls you down. The sun holds the planets. Gravity was intuitive. It was familiar. It was the first force every human being ever experienced, from the moment of birth. And it turned out we were wrong about its fundamental nature. Not slightly wrong. Not wrong about a detail or an edge case. Wrong about the basic category. We thought gravity was a force. It is not a force. It is the shape of space-time. We thought gravity needed mass to act on. It does not. It acts on anything that moves through space-time, and everything moves through space-time. We thought gravity reached out and pulled. It does not reach out. It does not pull. It curves the fabric of reality, and reality does the rest. This should give us pause about how much we think we understand about the universe right now. If humanity's greatest genius, Isaac Newton, could build a theory of gravity that was spectacularly successful for over 2 centuries and still be fundamentally mistaken about what gravity actually is, then what else might we be fundamentally mistaken about today? What other forces or phenomena that seem obvious and well understood might turn out to be something entirely different at a deeper level? This is not cause for despair. It is cause for wonder. Every time science overturns a deeply held assumption, it replaces it with something stranger, more elegant, and more true. Newton's gravity was replaced by Einstein's curved spacetime. The result is not a loss of understanding. It is a deepening. We see further, we understand more, and the universe reveals itself to be more extraordinary than we ever imagined. Light is our messenger in this process. Because photons have no mass, they are the purest test of what gravity really is. If gravity were truly a force between masses, light would be immune. The fact that light responds to gravity, bending its path, shifting its energy, arriving late through curved regions of space-time, is proof that gravity is something deeper than a force. Light strips away the confusion. It removes the mass from the equation and shows us what remains. And what remains is geometry. Pure, clean, beautiful geometry. When you look up at the stars tonight, every single photon entering your eye has travelled through curved space-time. It has followed a geodesic shaped by every massive object it passed along the way. Its path was bent, however slightly, by the mass of the sun, by the mass of the Earth, by the mass of every planet and star and galaxy whose gravitational field it traversed. Its frequency was shifted, however faintly, by climbing out of the gravitational field of the star that emitted it and falling into the gravitational field of the planet where you stand. That photon carries the fingerprint of space-time curvature in its path and in its color. It has been shaped by the geometry of the universe without ever being touched. And you, standing on the surface of Earth, looking up at that photon, are yourself deep inside a curved region of space-time. Time is ticking slightly slower for you than it would if you were floating in empty space, far from any mass. Your feet press against the ground, not because gravity is pulling you down, but because the ground is pushing you up, away from the geodesic you would naturally follow if nothing were in your way. You feel that push as weight. You experience it as gravity. But what you are really experiencing is the geometry of space-time refusing to let you fall freely along your natural path. Everything around you, every object, every beam of light, every ticking clock exists in curved space-time. The curvature is subtle here on Earth's surface, gentle enough that Newton's approximation works beautifully for nearly everything in daily life. But it is real. And for something like light, something with no mass and no possibility of hiding behind the Newtonian approximation, the curvature is the whole story. There is no force to fall back on. There is no mass to serve as a handle. There is only spacetime, curved by the Earth beneath your feet and the Sun 93 million miles away. And light follows that curvature faithfully, silently, without being touched. And that is how gravity changes light without touching it. Not by reaching out, not by pulling, not by pushing, by being the shape of the road that light travels on, by bending the fabric of existence itself and letting light do what light always does. Move forward at the speed of light along the straightest path available, through a universe whose geometry is curved by everything massive within it. That is what Einstein discovered. That is what Eddington confirmed in 1919. That is what Pound-Rebka measured in a university tower in 1959. That is what your GPS relies on every time you check your location. That is what the Hubble and James Webb telescopes reveal every time they photograph a gravitational lens, an arc of ancient light bent around a galaxy cluster, carrying the image of a universe billions of years in the past. Gravity is not a hand. It is not a rope. It is not a force at all, not in the deepest sense. It is the shape of space-time, and light, beautiful and massless, follows that shape wherever it leads, curving without being pushed, shifting without being touched, arriving late without ever having slowed down. That is the answer. And like so many great answers in physics, it is stranger and more wonderful than the question ever suggested it could be.